To start with, today we will begin with the discussion on this biochemical oxygen demand, biochemical oxygen demand, biochemical oxygen demand. Biochemical oxygen demand. Okay, just write. You can write it carefully. Right. There are two important things that I have said earlier in the classes. Let us begin. Let us deal with this oxygen demand part as such. See here, there are two differences, few differences to be made. One is when you are discussing biochemical oxygen demand. Before we go into the detail of biochemical oxygen demand, I want to discuss about two things. This is number one is this is very important for engineers outside or the environmentalists working outside, say civil waste or say sewage waste like this. Most in cases I in the last class also classes I also discussed this biochemical waste is the nature of the biochemical waste that I have said, the human excreta, say the dead bodies, then urinations, excreta, then dead bodies, leaves, dead leaves, all these comprise of biochemical oxygen demand. These substances are mostly in the nature, they call that they are of biochemical origin, and that is why since they have a very great demand. In fact, as I have said that mostly the environmental engineering started with sewage and sewage engineering. So basically there is a strong correlation of biochemical waste with environmental engineering. But as such there are few things to know about this biochemical oxygen demand or oxygen demand as such. What happens is there are one important part here is to this general biodegradation of wastes. This is what we would say biodegradation, biodegradation of wastes, biodegradation of wastes, right. The biodegradation of wastes, this can be very well be, if you just try to see this from this plot here, from this screen doesn't concentrate. Okay. So, it's mostly see this biodegradation of waste, we can write on a particular say equation which should be encompassing the complete reaction that actually takes place. So, see this is carbon being a very integral part of this kind of resources, this kind of wastes. Okay. A waste it's basically the nature of this is a nature, or this is the mostly what you would find as Ca, Hb, OC, ND, that is phosphorus and chlorine. This is a typical waste. This can be any waste or any organic compound that can be, but this one is not necessarily a biochemical waste. This is not necessarily a biochemical waste, in the sense this is the typical waste. This waste, a part of this waste, it can be of biochemical origin, another is biological origin, right, biochemical and biological origin. So, mostly these substances, this is what would be the waste would be generally made of. This waste when it is being converted as a biodegradation, it can be in the presence of oxygen, or in the presence of other substances on microorganisms, and oxygen, it would form two important things. Two important things is, you know, I CO2 JH2O K NH4. Remember this is NH4. This nitrogen in water would be mostly available as an ammoniacal radical, PO4 minus 3 minus plus M SO4 2 minus plus NCl minus. So, you can see this would be the mostly the reactions that we generally observe in cases like this. Here, you know, if we just see this, you know, in this place particularly, that, you know, this is the decomposition taking place with in the presence of the microorganisms. Now, the two things to understand here, why these microorganisms do it. In nature, nothing takes place, nothing happens without a cause. Nature would always form anything that forms in nature. Nature is basically always takes something with a cause, and nothing takes place as an accident, or nothing takes place just as it is. I mean, without a cause. Everything has a cause. The cause here, the microorganisms need them because there are two things. First of all, this waste here would be mostly in the form of, possibly in the form of solids, or also they may be in the form of liquids dispersed in water. Okay. So, there is just like, you know, urination is a biochemical waste which is a liquid, but it will be dispersed in water, number one, or it can be solid waste also. So, in cases like that, if it is a solid waste, microorganisms would have to break them down so that they remain soluble in water, or at least, you know, not, even if it is not soluble, in an immiscible state in the water, and in a liquid form. Immiscible does not mix with water, but remains in a liquid form, or it remains as a soluble form in water. These two things are very important, only because in such cases only a single or microorganismic cell, can draw it as a food by an osmotic method. Understood? So, the osmosis is take place when there is a change in the potential from the from outside potential to, from positive to negative potential it take place, since that there will be a potential difference. So, the substance from the external environment would enter the cell. Okay. So, this is where, you know, the microorganisms need to break them down. This remains as the most important reaction. I mean, that can be exemplified as the possible as the cause for the total human life, total organism life, or total organic say the population that we see, is basically just because, you know, this has resulted into a wastes getting decomposed, and this is how, you know, otherwise just consider the thing, if the microorganisms should not have been there, the waste should not have decomposed at all. Okay. So, this is where the microorganisms play a very, very important role, and that is how it gets you know gets gets decomposed in two ways. The first of all, this process would be known as, one is called this you know, into breaking down into just see this breaking down into a say this inorganic molecules. We called it as mineralization, and the second one is we would call this as biotransformation. Biotransformation. See this one here. This one is inorganic molecules, mineralization, whereas this one is the biotransformation in the form of ions, in the form of ions, mostly forming in the place of, in certain extent, in biological materials. So this should be mostly, it is not in the molecular form, it would be in a radical form like this, which would be mostly readed like this. So here you can see this would be mostly in the biotransformation. So two processes essentially take place, and this takes place only because there the microorganisms are active, the microorganisms are leading these reactions. That is because they are agents of these reactions, and they are taking place in the presence of oxygen. So this is one reason why oxygen gets depleted, in most of this, in the water body itself. Apart from this, if we just observe now, if we just try to observe it now, here in a much better detail now that I can see it, here there are two things that it would be observed. Let me explain you a little bit on this. Say if a waste is introduced, at say this is if you just see the plot here, if the waste is introduced, just 1 minute. If the waste is introduced here, you can see now this is where the waste is introduced. Suppose any from any process, or the waste is being dumped here. Say here it is, waste is being dumped here. So here at this point the waste is being discharged here. Okay. Now here, as you can see, this is the saturated level of oxygen in this water at this particular salinity. This is saturated level of oxygen at particular salinity, right. This is the water, the waste has been introduced in this. What would happen is that this saturated level of oxygen, if you just say this dissolved oxygen, and if you say it time say in days, if we just try to see in 1 day, 2 days, 3 days, 4 days, 5 days, like that, 6, 7, it can carry on. In fact, it can carry on. So if we just observe this curve now, depending on the nature of the waste, you see this, the depletion of oxygen in the water would take place. I mean, the rate of depletion of oxygen would depend on the nature of the waste. Remember this, nature of the waste. So you can observe a plot like this, you can see this is like this, you can see somewhere it is not going like this, say this is. So if you just observe, if you just try to observe this, some of the substances here, some of the substances like here, you can see this is mostly you can find out mostly this, mostly if you observe this is mostly this carbohydrates should be forming this kind of plot, right. This is just a notional. I mean, don't try to always try to say special kind of carbohydrates may remain may follow a certainly different curve. This is just to for a comparison. Say here this one is this is this is say if you just closely seeing this, if you this is be amino acids, okay. This one would be say fats and oils, So this is say tertiary and quaternary. This is say tertiary and quaternary, tertiary and carbon and nitrogen compounds. Okay. Similarly, you can see this would be ethers. If you see this might be, this is the mostly that benzenes. So this is what this would be, generally you will not find in any textbook, but this is what would be the mostly the nature of the plots. This is what would be the mostly, you can see this would be the mostly the plot. So this figure is to suggest that is depletion of oxygen in water due to the presence of waste. We can see this if you just try to observe this now. Here in such cases interestingly, here when we are talking about most of this biochemical waste, this mostly the biochemical waste would be around this region. This is mostly the biochemical region. You can see this, these are all the biological other wastes. Other wastes should be here. And so mostly you can see this biochemical wastes, this would be primary level hydrocarbons. Mostly this would be the formation of this would be, this one would be showing the biochemical waste. So this is about the biochemical waste, this is about this biological wastes. All right. Biological and biochemical waste, this you can see the relationship. Now remember one thing, I mean this is for most of the pollution engineering or in the wastewater engineering that we generally discuss about, mostly we discuss about this region only. This is the hashed portion that we generally discuss. That the other portions here you can see if this can be explained like this would be the total biological wastes. So this would be biological waste. Okay. So this is what this is what we generally observe at. This is the depletion that takes place. This is how the behavior of different wastes in water. What we are observing here in this case, if there are no further addition of water or no other source of oxygen being supplied to water, the amount of oxygen in the water would continuously go down and go down till it reaches almost zero, right. This would be clearly if the waste concentration of waste is very heavy, in such cases the oxygen concentration of oxygen in the water would go down as much as zero, to zero. So there will be almost no water, no oxygen available in the water. This is one part that is of great significance for our work, for our study here. We would also see that this whatever we just see, there are few things that I want you to understand. This is the fats and oils. Fats and oils are less biodegradable than carbohydrates. Fats and oils are less biodegradable than carbohydrates. Okay. This is number 1. Then there is secondary hydrocarbons. Secondary hydrocarbons show better resistance to biodegradation in comparison to alcohols and aldehydes or organic acids or organic acids, because they are less prone to oxidation. Because they are less prone to oxidation. Third, if we just make this tertiary and quaternary carbons and nitrogens have less ability than primary and secondary carbons and nitrogens. Right? You can see this. This is as these are going for higher bonding, increased, it is going in mostly, if you think of organic chemistry, where you start with alkenes, alkynes, right, then hydrocarbons, carbohydrates, alkanes, alkenes, and then you finally go about this benzene ring, and further then you go go particularly into hydrated metal hydrocarbon complexes, all kind of thing. Wherever you are going from one stage to another, their biodegradability would be going to go down, would be less continuously, less. This is what is very important for us to understand, and forms a primary basis for environmental control. Ethers are practically non-biodegradable. So, these organisms do not have almost any effect on ethers. So, these ethers are, say this 5 ketones are less biodegradable than ketones are less biodegradable than aldehydes, right. Ketones are less biodegradable than the aldehydes. Okay. So, you can see this, the what I mean to say here, remember one thing, never I have said that all these substances can be only out of biochemical origin, they can be outside also, and primarily outside, because most of these substances are outside the biochemical range. They are not produced mostly by this biochemical substances. Biochemical substances are mostly related mostly related to organic acids, secondary hydrocarbons, primary hydrocarbons, secondary hydrocarbons, some of them aldehydes, organic acids, some substances like that, but not in the higher organic groups. Okay. So, having said all this thing, this is particularly, there are few processes that actually reduces, there are biodegradation is this is biodegradation. All this, in the process of biodegradation that we have said, mostly for all kind of wastes, is this one is certainly the oxidation. One process that leads biodegradation is oxidation, reduction, hydrolysis, substitution, elimination, right. These are these biotransformations, biodegradation led by biotransformation. So, biodegradation led by biotransformation, I mean the transformations that take place, it can be oxidized, it can be reduced, it can be hydrolyzed, the addition of water, substitution, one group replacing other, one organic group replacing other, one organic group replacing other, elimination, we find says removal of atoms from from adjacent carbon, and condensation. In this is condensation where you can see this production of larger molecule, production of release of electrons, as you know, this oxidation and addition of electrons. In all these cases, the number of several microorganisms can be an agent. This is microorganisms microorganisms as agents. So, microorganisms not essentially does only only in the case as we have seen not only does decomposition of wastes, it can decompose, it can transform also. But the most important thing, that is this more than bio decomposition, what we have been talking about biotransformation, this term is more appropriate, because it is not necessarily always oxidation would take place. Okay. So, having said all this, these are the most important things about this this is when you are talking about the oxygen demand and particularly the oxygen demand in cases of biochemical oxygen demand mostly. So, remember one thing is so here we can say one thing here, it says biological oxygen demand would be here what is biochemical oxygen demand, biochemical oxygen demand plus non biochemical oxygen demand say from biochemical, say this is waste or living organisms, waste or living organisms. So, we can see this waste or living organism, we can observe that this biological oxygen demand would include this. So, here a biochemical oxygen demand plus this non biochemical oxygen demand waste out of the source of biochemical sources, and also some of these living organisms, plants and plant species and animal species, or any kind of species that you can think of. So, this is the total biological oxygen demand. In fact, when you are finding COD, we are finding COD, mostly we are finding COD is almost similar to this biological oxygen demand. Biological oxygen demand. COD is essentially biological oxygen demand, right. So, here this is once we make a distinction like this, you can see now that there are essential distinction that we have made in most cases, as we have known for that most of these biochemical sources, most of the substances of biochemical origin and also of biological origin can be easily decomposed into other hydrocarbons, and most the very convenient way of saying this is that the biochemical waste plus oxygen is plus oxygen, this is microorganisms the microorganisms also sometime we must also need a source of energy. We need a source of energy. Source of energy is also very important. So, sunlight, I mean either sunlight or any other substances, any other sunlight or enzymes, different enzymes that we can generally find out. We generally find out that they can decompose into CO2 plus H2O plus new cells plus stable products. This is mostly This is mostly the aerobic reaction. In oxygen. As oxygen begins to deplete, as the oxygen begins to go down, the same reaction, this same reaction would be, say this oxygen is a biochemical waste. Remember this biochemical waste or biological waste, do not make any distinction, biological waste, biochemical or biological waste, biochemical waste or biological waste, getting immediately converted, in the presence of this microorganisms remaining there, but generally for all your information, the microorganisms also change. These are aerobic microorganisms, they would be mostly anaerobic microorganisms, right? Aerobic and anaerobic microorganisms. Mostly in all these cases, we find that CH4 plus new cells plus unstable products. All right, you can see now, you can see here unstable products, right. So, you can see that how best we can basically explain that this situation here, that where it is when the water is having when the waste is immediately dropped and the oxygen is not yet depleted at this point of time, we will find that first one, this particularly the aerobic reactions taking place. Okay, aerobic reactions taking place as the oxygen level would be decreased, also the sources of energy would be decreased, sources of other sources of energy, such sunlight getting decreased, or we are not allowing other energy source to go into. In such cases, this is generally in the deep of water. If you consider in the depth of water, if you just see the top column of a pond would be mostly the reactions that we generally observe would be aerobic reactions. But as we go in the depth, when there is a less of sunlight and also the water is depleted of oxygen, in such situation we would find the second state, that the biochemical waste or biological waste getting depleted by this inorganic depleted by the microorganisms, anaerobic microorganisms, in the absence of oxygen and sunlight, to form carbon dioxide, methane, new cells and unstable products. So, this is how mostly these organic substances get decomposed in water. Okay. Now, having said this, that there is a very standard thing that we generally find out, that 5-day BOD test, say one, okay, the the parameter in terms of reducing level of oxygen, the parameter that explains the nature of waste in terms of reducing level of oxygen with time is known as BOD, right, biochemical oxygen demand, What is the demand of oxygen, or in other words, what is the demand of oxygen by the waste? What is the demand of oxygen by the waste? One very conventional way of using this 5 BOD, this is BOD is called 5-day BOD. It is called BOD 5 or 5-day BOD. Why BOD 5? Let me explain this here itself. This is what, if you just observe a particular waste, if it is a biochemical waste, mostly a typical biochemical waste. Remember this is a typical biochemical waste. Okay. This is biochemical waste. So, this is, you can see this biochemical oxygen demand, this is what is in relation to time. If you just observe, first most for say 5 days, if you say 1, 2, 3, 4, 5, mostly if we are trying to observe this is the DO. As soon as it is dropped into the water, before till that time the water does not have any oxygen demand. As soon as the waste is dropped into that, the oxygen demand is rising, but at a increasingly flatter rate, right. The rate would go down, the rate would go down like this, the rate would go down, but it would still, the demand of oxygen would be higher. The oxygen would be so demand of oxygen would be like this. So, what happens now is, here in such cases it is observed generally mostly at 20 degree centigrade, at 20 degree centigrade, at 20 degree centigrade, without other sources of oxygen, thereby making sure that there are no other sources of oxygen supplied or given to the water. In such cases, what happens is, this is what would be, this is what is this, this is how this BOD would increase, biochemical oxygen demand would increase. And then finally what happens after 5 days, this zone, this is particularly what is observed is, this particularly is basically the decomposition of the this is decomposition of carbohydrates, like any kind of waste. Carbohydrates, say if it is a if it's a dead body, say it's a dead body, if the dead body is generally thrown into water, or if it is rotting in the water, first 5 days we observe that this oxygen, the requirement of oxygen is just to oxidize these hydrocarbons, these carbohydrates. These carbohydrates would then what we observe now is, after 5 days at 20 degree centigrade, we generally observe that this particular the demand of this carbohydrates, or this we call this carbohydrates, or we call them carbonaceous products, would remain almost constant, but here we would find another increased value of, we will find that there is another demand increasing at this point of time. At this point of time we are finding another demand increasing. See, this would be mostly, this demand can continue for a long time. This is called nitrogenous substances. So, nitrogenous oxygen demand, and this part is this is nitrogenous biochemical oxygen demand, NBOD. This one is known as CBOD. Okay. This should be known as carbonaceous biochemical oxygen demand. Carbonaceous biochemical oxygen demand. Okay. There is carbonaceous biochemical oxygen demand. So, what we find out in BOD5 essentially is carbonaceous biochemical oxygen demand. All right. We find out mostly this carbonaceous biochemical oxygen demand. This oxygen demand would take place till what time? Till the time till the time the oxygen is completely depleted out of water. After that, there would be decomposition would almost go down very slowly, unless there is a source of oxygen or anything like that. Till that point of time, the decomposition would not take place. Okay, I think so we will stop at this point, right? 1 minute. We will stop at this point. I mean, there may be I have asked for 2 classes in fact. So, this is we are just now at this point of time. So, here we can see now that if we are given a class, we will take the same class, otherwise we will just be off here because so we were discussing about this BOD, the biochemical oxygen demand, and then let us find out the initially in the beginning that we have said. So, there is a determination of one important thing, that is determination of BOD. The standard, let me do it by step by step. Say this is number 1, collect some 30 to 50 milliliter of wastewater sample. Remember this wastewater sample in a stoppered bottle, if required by the nature of the wastewater add distilled water or water without BOD of its own to make the solution up to 400 ml, up to 400 ml. Determine the dissolved oxygen. Otherwise, if the BOD is very low in a sample wastewater, if a BOD level is very low in sample wastewater, suppose you generally have a water which is having a very low BOD of its own. So, in such cases you might find at the end of the 5th day there is no depletion of oxygen, because the reaction rate is so slow that no discernible change has taken place, no observable change has taken place. So, if you put BOD, a seeded BOD, if you just use some water having its own BOD, then in that case we find out that the reaction takes place at a faster rate, and we will observe that the oxygen the depletion of oxygen is at a faster rate, and we find a considerable decrease in the oxygen decrease in the level of oxygen in the water. Okay. So, this is why this is called seeded. This is the water having having BOD of its own is known as the water having BOD of its own is known as seed, and the method is known as seeded BOD test. This is known as seeded BOD test. The experiment, the method, seeded BOD test. So, in such cases what we find out is, we can very well write is like this: BOD of the mixture into the volume of water, the water of mixture, volume of the mixture is equal to BOD W wastewater, volume of the wastewater, plus BOD of the seed, BOD of the seed and BOD of the seed and volume of the seed, right. So, in such cases there are other things that we can find out is Vm is equal to Vw plus Vd. So, you can find out one this thing here, 2 here, and as you can find out from here, this is, if you just can find out like this, we can say this BOD of the waste, BOD of the waste can be written like BOD or BOD of the mixture divided by Vm divided by Vw plus BOD S as an integration. Here it is this it would begin from L0 into T, LT, L0 into T when there is no demand. There is no demand, this is this would begin from here, and this one is minus K KT as you can see here. So, here it is log LT, this is L0 to LT, and this one is minus KT, or we can find out that this would be essentially this is what we can find out, LT is equal to LT would be LT is equal to L0 into e to the power minus KT. Minus, so it comes LT log LT divided by log L0. So, this one is, if LT by L0 is would be e to the power minus KT. So, L0 you are bringing in there. So, L0 into e to the power minus KT. So, this one is, it says that at any point of time L0 is known as the ultimate carbonaceous. Remember this carbonaceous, ultimate carbonaceous BOD. This is known as ultimate carbonaceous BOD, which is nothing but is, you can see log say LT, this is log L0, or say this one is e to the power. So, you can find out this. So, this is log LT divided by L0. So, you find out like this. So, here as you can see, this one is the ultimate carbonaceous biochemical oxygen demand, ultimate carbonaceous biochemical oxygen demand. So, in case if we are just plotting it now, this this you try to see this. BOD remaining, and if we just put time here, BOD remaining, and if we put time here, this we can see that may not require to decompose with the help of oxygen or in the presence of oxygen. So, in such cases this is not absolutely. What is more important in cases of this are the metal solubilities. We would see this in one of these classes, metal solubilities. These metal solubilities deal with this particularly the soluble in a partial pressure condition in water, how one metallic ion gets released in preference to another metallic ion, right. And in such situation we would see this, as I have said, in many cases the speciations become different. Just let me give you a simple example here. This may give you a simple example here, where we could observe this particularly this metal solubilities. If you just see this metal solubilities here, you can see this, say, as you can see, mostly dissolved molecules of inorganic substances break into charged ions, break into charged ions, right. Break into charged ions. These charged ions, you can see this is charged ions is cadmium. This is quite interesting to observe that cadmium in the presence of chlorine ion can form a reversible reaction of CdCl. See this CdCl plus, it can also CdCl, this CdCl plus would be then Cl minus can form CdCl2 plus Cl minus can CdCl3 minus, this CdCl3 minus can form with Cl minus